This is the explanation or pre-lab for the specific heat of a metal. There is a post-lab in here that you might want to delay until you've actually done the investigation. In this experiment, you're going to determine the specific heat of a metal sample by finding out how much heat a measured mass of hot metal transfers to a measured mass of cool water. We'll know the initial temperature of both substances, we'll know their mass, the final temperature of both, and the specific heat capacity of water, which is 4.184 joules per gram Kelvin. Intuitively, we know that heat flows from objects at high temperature to those at low temperature, as shown here. This hot heating element is generating heat, and it is flowing into the cooler pan, or whatever inside that pan. Intuitively also know that different substances have a different capacity for heat. For instance, if you heat an empty pot, it's going to heat up very, very quickly, and if you touch it with your finger, it's going to scald you pretty fast. On the other hand, if you have a pot full of water, it will heat up much more slowly. Water has a very high capacity for heat, and that's measurable. We measure the specific heat capacity of substances. Specific heat capacity, which we shorten to specific heat, and it's indicated by the symbol capital C. It can be measured so that we can calculate exactly how much heat in joules is needed to raise the temperature of 1 gram of a substance by 1 Kelvin, or 1 degree Celsius. Here's how you will do it. You'll measure the mass of a metal slug, and the metal slug has a little knob on top that you can grab, particularly with a pair of tongs. In boiling water, you're going to heat the metal slug to the boiling point, about 100 degrees. It won't be exactly 100 degrees Celsius, and you will measure that temperature. You'll put the hot slug then, using the tongs, into a measured mass of cool water that you've measured the temperature of, so that you know the mass and the temperature of the cool water before it gets the metal. And that'll be in a calorimeter, which is probably just a styrofoam cup that has very good heat barrier between the water and the outside. It's well insulated. You're going to find the temperature that the water warms up to, or if you wish, that the metal cools down to, and it will calculate the temperature changes in the specific heat capacity. This should all show up in your lab notebook. There are safety considerations, of course. Always treat a hot plate as if it's hot, and always treat beakers as if they are hot. Avoid burning yourself. Keep the beaker of hot water on the hot plate. That not only keeps the heat in the water and prevents it from losing it, but it also is a kind of a warning, and you won't want to touch it if it's on the hot plate. Wear your apron and your goggles, and wear closed-toed shoes. You'll be working with glass and hot liquids. Use tongs to transfer the metal slug very carefully. Keep a firm grip on the slug so that it doesn't drop back into the hot water and break the beaker. Avoid splashing hot water on yourself or anyone else, or even on the table. Never heat the slug directly on the hot plate. Some of these have a very low melting point, and they could melt. Here's your post-lab. You should have the following data: the mass of metal in grams, the mass of empty cup, the mass of the water and the cup, the initial temperature of the hot metal, and the initial temperature of the cool water in the cup. And of course, the final temperature is the temperature that the hot metal cools to and that the calorimeter water warms to. Let's talk about your calculations. If you subtract the mass of the cup from the mass of the water and the cup, you'll find the mass of the water being warmed. You will need that to calculate the specific heat capacity. If you subtract the final temperature, which is down here at the bottom, from the initial temperature of the hot metal, you'll find the change in the temperature of the metal. And if you subtract this final temperature from the initial temperature of the cool water, you will find the change in the water temperature. Actually, it'll be a positive number because the temperature there is going up. Now, how do you calculate the specific heat capacity? We'll use some sample data here. We know that the heat that is gained by the water is equal to the negative value of the heat that is lost by the metal. If the metal loses 1,000 joules, then the water gains 1,000 joules. We also know that the Q, the heat, is the mass of the water times the heat capacity, specific heat of the water, times the change in temperature, and therefore that's going to be equal to the mass of the metal times the specific heat capacity of the metal, which we're looking for, times the change in temperature of the metal. And since this is a positive number, the heat in the water is going up, this is losing temperature, so the metal Q is a negative number. We then divide, to find the specific heat capacity of the metal, we divide the mass times the product of the mass, the specific heat capacity of water, and the change in temperature of the water by the mass of the metal times the temperature change of the metal. We're going to plug these numbers in that we have generated over here on the left. 150 grams of water, 4.184 joules per gram Kelvin. See, I wrote that down here on the bottom for the specific heat of the water, and 4.3 Kelvin temperature change for the water. And then here's our negative number here because we had a negative change in the temperature of the metal, which has 50 grams and a negative 72. So the specific heat capacity here, the negatives will cancel out and we'll have a positive number. When we do the arithmetic, we find the specific heat of this metal or alloy is 0.749 or 0.75, probably with 4.3, two significant digits here, joules per gram Kelvin. Now you plug in your own numbers from your lab, from your investigation, your numbers in units, and then check your mathematics with your partners. And please remember, when you're doing the specific heat capacity of a metal, the answer has got to be less than 1.